So, yeah, quantum computing. So the assumption here is that you don't have a background in quantum computing and you know some basic algebraic manipulation. Let me just stop my video. And so we'll cover concepts, some quantum concepts, algorithms that are some famous algorithms, foundational basic algorithms, and use cases. Okay, so we'll not cover implementation of quantum computers, the implementation of quantum computers, quantum gates, quantum circuits. Oh, okay. Okay, guys, sorry. This one is definitely wrong. We'll not cover the implementation of quantum computers. Okay, let's begin first with the concept. Okay. Yeah, so this is the most beautiful experiment in physics. This was the voted as the most beautiful experiment. This one illustrates the nature of quantum particles, and which is also the basis of quantum computing. Okay, so imagine you have this a gun with bullets, and then these bullets, you know, these are large, okay, typical bullet, and you have here a wall with two holes. Okay, so and then one of the hole is open and the other one is closed. So if you fire the machine gun into this wall, some of those bullets at random, some of those bullets will end up going inside the hole, and then and there will be a concentration of bullets in this part of the wall, and depending on where it is on the wall, some part will have more bullets compared to other parts, like this one here at the edges, or the this one here is only a few bullets are hitting. So in other words, they have we then have a distribution of the number of bullets landing on this area of the wall. Now, if you close this and then you open this, you will also see the same pattern, but in this part of the wall. Now, if you open both of them, then you will see this distribution of the number of bullets hitting. So this part here, you won't see any bullet landing, or zero bullets. Now, if you have a water wave, then same process. You will see that if you open both slits, then you will see this pattern in this wall, and the reason for that is the reason why we have this pattern is because the water waves, being waves, they tend to interfere constructively when you have a crest and a crest, or a trough and a trough, and destructively when you have a crest and a trough. So during in those areas where the crest and the trough meet, you will see that the water hardly moves, doesn't move. Now this one here, the third one, is an electron gun. Okay, so it also fires bullets the same manner, electrons. And the curious thing to see here is that um, the pattern that it makes in this uh, wall, assuming this is a film, you will see that it also behaves like a water waves. Okay, electrons behaving like water waves. But the thing is, there are already experiments which show that even if there is just one electron that is fired through these slits here, the single electron will also form an interference pattern. So in other words, the electron interfered with itself, so it behaved like a wave. And so imagine the electron um, in, interfere with itself. It means that the electron passed through these two slits. Okay, so that's one way to explain it. It passed through these two slits and interfered with itself. And this is the basis of superposition. So in quantum computing, we are going to discuss about qubits. Qubits behave in like that. We can put a qubit in superposition, and which and it turns out it has a lot of implications. So, so the qubit. Okay, so in classical physics, we have a bit which has a value, a definite value. It can be 0 or 1, and but in a qubit, the qubit is different because it can be made to behave in superposition, which means that it can be in the 0 state or in the 1 state or anything in between. Okay, so this one, the one that you're seeing here, is called a Bloch sphere, and it's a mathematical representation or visual representation of a qubit. And the circle that you see here, the reason you see a circle here is because the what you call this, these numbers A and B are complex numbers. So this one here is the complex plane. And we tend to, and also the by definition of the Bloch sphere, the what you call this, the length of this vector here is 1. So the square of the modulus is equal to 1. And we do that in quantum mechanics because the square of the amplitudes are the probability of when you measure a qubit, it is the probability of getting, like for example, a 0 or a 1. So in this case, if you measure the qubit and it gives you a 0, so the probability of getting a 0 is given by this by the square of this number here. Yeah, so A and B, it can be doesn't need to be 50-50. It can be as long as it can be anything as long as the sum is equal to 1. Okay. So when you measure a qubit, it is different from the way you for example, if you have an experiment and you have a coin, okay, like a classical coin, when you flip it, and then when it lands, it will give you a heads or tails. Okay, so when it lands, that's like the concept of measurement. It will give you a definite value, which is 0 or 1. Okay. So, oh, sorry, heads or tails. And then when you measure it again, okay, you get it in there, and then it will give you another value. But the difference between a um, a classical coin and a quantum coin, imagine you have a quantum coin, you measure it, gives you a head. If you measure it again, it will still give you a head as long as you measure it very quickly, okay? Because um, so that's the concept of measurement. When you measure the qubit or a system, a quantum system, it will collapse the state of the system into a definite value, and that value is governed by the probability of getting that state. Okay, and it stays in that state if you measure it quickly. Otherwise, it will obey the laws of quantum mechanics. It will evolve using the Schrodinger's equation, and you might get a different value next time. So measurement causes the wave function of the system to collapse to a state, okay, which is the result of the measurement. Another concept of quantum theory is entanglement. So it's possible to have two quantum particles to be entangled with each other. So which means that when you measure one of the particles, it will automatically give you the other particle will automatically have a definite value as well. So, for example, in this one here, if you measure it, and if one is red, then two must be blues. Something is so. This one is the mathematical representation of that superposition. So where the probability of having a red-blue combination is the square of A, and the probability of having a blue-red combination is the square of B. Now, if you measure it and you get the first qubit as red, then automatically the other qubit collapses to blue. And in the same way here. So that's entanglement. The curious case about entanglement is that it obeys these laws even if the two particles are very far from each other, which in some sense, if you think about it, will violate the requirement of special relativity that information cannot travel faster than the speed of light. Okay, so, but that is how nature behaves, you know. So far, quantum theory hasn't disappointed us. So it's something which it's hard to explain. There are a lot of explanations out there, but that's how it behaves. Okay, so we'll not go into that, but that's something which is very useful in quantum computing. Okay, quantum tunneling here is this. So this also very curious, interesting property of quantum systems is that they tend to be able to tunnel. Okay, so for example, in a classical if you have a classical particle, and suppose this is your potential energy, and your particle only has a kinetic energy that is less than the potential energy, then it's not possible for these classical particle to be seen on the other side. Okay. However, in quantum theory, it might not be the case. So there is still a probability that the particle, even if this energy of the particle is less than the potential barrier, which is the energy of this barrier, there is a possibility for this particle to be seen in the other side. Okay, so that's quantum tunneling. And why is it very important? So it's very important because the electronics that we have, for example, the chips that we manufacture, which obeys Moore's law, they have a physical limit. Okay, so which means that we cannot pack as many uh, many transistors as we can indefinitely into smaller and smaller area because of this. Because if the because the transistor is nothing but a gate or a switch which on off and off. So if a transistor will be in a state off, then you cannot have electrons moving across. And when you turn it on, the electrons can cross that switch gate. However, if the what you call this, the width of your gate of your switch is already approaching 1 nanometer, then it's possible for quantum effects like tunneling to already manifest itself, which means that you cannot have a switch anymore because the transistor will just flow through, just tunnel through your switch. And all the more reason that we need to have a way to compute things, and this is where quantum computers come in. We what we now do is embrace this fact that we cannot go smaller, so we just have to embrace the fact that okay, let's make use of this apparent weakness into a strength. Okay, so we'll do quantum computing. Okay, so that's I think the more important, most important concept in quantum physics that we need to know. And now let's go to quantum algorithms. Okay. So quantum computing, if we have a powerful enough quantum computer, then it is predicted that it can factor out, or it can crack the two most used algorithm in encryption today, which is the RSA and the elliptic curve. Okay, so RSA is usually used in the default, but if you have lower power devices, then it's usually the elliptic curve cryptography that is used. But the thing about this two seemingly different encryption schemes is that they are actually they have something in common, and they are instances of what is known as a hidden subgroup problem. And because of that, an algorithm called Shor's algorithm is able to solve or able to crack them. Okay. Now, ordinarily, if you don't have a quantum computer, and this is what I read, it takes about, for example, the given speed of this laptop takes about 300 trillion years to um, decrypt RSA, that 2048 bit RSA. Okay, so which means if that's true, then it's really if without a threat of quantum computers, then we are really secure, right? It's really secure. But because there's already this threat, which can theoretically, which is predicted to decipher this encryption, then we are now we should now be in the lookout, okay? Because nation states that are very interested in each other, that learning each other's secrets, are already trying to save those encrypted information, okay, somewhere, store it somewhere, in the hope that when they are able to get their hands on a quantum computer, and they will be able to decipher and find out the secrets that's in this encrypted data. So quantum key distribution is another important application of quantum computing. So whenever you want to send a message to another person in private, okay, there you usually agree on a secret key, okay, so a secret key in order to encode your messages, okay. Now, if it's possible for you to meet face to face and talk in private, then give the key to each other, then that's good. But if it's not possible, like for example, one of you or both of you are different parts of the on Earth, then probably the only way for you to communicate is via the internet. And in order to secure your communication, so that for example, I can send a key to Asher, then I will use what is known as the public key cryptography. Yeah, so but if you have a quantum computer, usually public key cryptography are based on this algorithms like RSA and elliptic curve. Then if you have a quantum computer, then that would not be good. So in order to secure, even if you're miles away, then quantum effects like entanglement, you can use it in order to send your keys. So here I'm just so this one here is a visualization of the Bennett and Brazard QKD scheme, or QKD means quantum key distribution. And according to this scheme, there is a this is the probability of detecting an eavesdropper. So for example, if I'm talking to Asher and then somebody like Eve is intercepting our photons, then the probability of detecting Eve is very high. Now, for example, if Asher and I agree that okay, let's compare our bits, n bits, let's say 10 bits, where n is equal to 10, then the probability is of detecting an eavesdropper is very high. It's about more than 90%. Okay, so that's a very high probability. So this is very useful in um, quantum in encryption. Next is optimization. So this one here is I'm going to discuss this because there are two ways, at least two different models of computation, which are equivalent to each other. One is using what is known as the quantum gates, and the other one is using what is known as the adiabatic quantum computing. Now, in here, I'm describing the adiabatic quantum computing because this is really very curious, and it's like I mean, this is really interesting because um, you're making use of how nature behaves, because nature tends to minimize something, tends to minimize the energy in this particular case. So by making use of that behavior of nature and encoding your problem into a physical system, you are able to um, solve your optimization problem. And this is really very curious because I think in before, I think it was in 2004, early 2000, that I heard about parasitic computing. And parasitic computing is, you're trying to solve a optimization problem without the other computer knowing that you're actually solving a problem. It's very curious. You just use the protocol to be able to solve the problem, and this one is probably similar to that. You make use of it's like hacking nature. You make use of the behavior of nature in order to solve your problem. So here, uh, you have a optimization problem that you try to map to a energy. Okay, and because nature tends to minimize itself, when the energy is minimized through a physical process, you then map this energy to an eigenvector. Now, the elements of this, or this eigenvector, which can be expressed in terms of these variables, can then be mapped into your original problem and to solve your optimization problem. So here is like the implementation using traveling salesman. Okay, so I'm not going to go into this, but this is how it's done. Okay. And yeah, so this one is also in relation to what I was saying earlier. You make use of a process called quantum annealing. So when you have a ferromagnetic material, and then you you heat it. Okay, when you heat that ferromagnetic material, what happens that the the spins of the electrons of that magnetic material, they tend to be arranged randomly. But then as you try to um, uh, to cool the system, and so in this particular case, you you try to you try to vary the um, um, the magnetic field slowly, and what will happen is that this electron spins will tend to align themselves in such a way that that oh sorry yeah so in such a way that the they will align themselves such a way that the total energy becomes minimum. But this one here is quantum annealing. What it tries to do is actually use the what is known as the quantum tunneling. So here you have this these hills and valleys that you see here. This is the energy landscape, and what you're trying to do is what the system is trying to do is trying to find that minimum energy. So in classical, there's an algorithm called simulated annealing, which is a classical algorithm. What it does is explore this hills and valleys, and if your algorithm sees a minimum value, it it will try to determine if it's a minimum value, and by taking a look at this first, it will try to climb this because it doesn't know yet it's the minimum value. So there is a hill climbing involved, and then here you go to another minimum value, and then you climb again, and after that you'll be able to determine which one is the global minimum. But for quantum annealing, what it does is it makes use of the quantum tunneling feature of quantum particles. So it's able to tunnel through this energy landscape and and um, and be able to determine the minimum. Okay, so as long as of course, not every energy landscape can be tunneled. As long as uh, the the width is sufficiently what you call this sufficiently uh, small, then it will be able to tunnel. Now another algorithm that is very popular is the Grover's algorithm. So imagine you have a telephone directory, and then you want to find. Okay, so this telephone directory has name and number. Okay, so name and number, and this telephone directory doesn't have a reverse index like number to name. Okay, it just only contains name and number in alphabetical order, the name. Okay? So for example, if I want to find Brian's telephone number, then I will just use find it like I find an entry in a dictionary, and it's very fast. Okay. However, if I am given a number and I want to determine uh, whose number this belongs to, then that's a different story, because um, if you're very lucky, then that number will be the first entry in your telephone directory. If you're very unlucky, then it's possible that that number is the last entry. It's possible it's not even there in the telephone directory. So, on the worst case, if you have a million of these entries in your telephone directory, okay, so like you have a very big nation, then it will take you will have to read one by one the entries. Okay, so if there's a million, then in the worst case, you read all the 1 million entries in order to determine whose name is attached to this number. But on the average, you'll just read 500,000 entries. Okay, now with Grover's algorithm, you can actually do better. No? So with Grover's algorithm, first you it doesn't assume that you have a sorted database. It's just database is there, but you're trying to find this this number. So Grover's algorithm can do it for you in a in square root of n, where n is the number of entries. Okay, so there's another way of looking at it. So suppose this is your, all of these dots here are your entries in your telephone directory. Okay, and you're trying to find a number, the name of that number. Okay, now there are 2,500 dots in this area of square, but if you try to find that specific name attached to that number, then in the worst case you will have to examine each of these dots. Okay, 2,500 in all. But with Grover's algorithm, you will just have to get one of these layers. Okay, that's the number of dots that you have to take a look, and the number of dots is just the square root of n. So in this case, only 50. So that's the speed up that is afforded to us by Grover's algorithm. So it's a powerful algorithm. And the thing about quantum computing is that it's the way it's programmed, like the Grover's algorithm, is very much different from the way we program it in classical computing. So in classical computing, it's usually divide and conquer, you know, those, and you have a looping involved. But in here, it's different. The way it was created, the way the technique is different. It's using concepts in a mathematical um, framework called Hilbert space, which is the mathematics of quantum mechanics. So in Hilbert space, this is the space of vectors, and so that's why you can see that vectors are nothing but, I will just say not, I will not say nothing but vectors are um, most of the time represented as arrows. Okay, and as you can see, you're trying to find this this state here, which contains your number a, the index, and this is you begin with a superposition of all possible values of your indices. So from 0 to 2 to the n minus 1. So this one is the vector here. And then what you do is to rotate this vector, a few times, okay? When I say a few times, it's like the square root of n. So if there are 2,500, then the square root of that, so 50 times, okay, you rotate, and then you will have a probability of getting the answer, very high probability of getting this answer here. Okay, so that's Grover's algorithm. So as you can see, the way things are programmed in quantum computing is different from what we are used to. Okay, and it's still difficult. Yeah, one of the applications also of quantum computing is in machine learning. So as you can see here, this was taken from a book by Peter Wittek. Say, yeah. So these are the algorithms, and it states here that if it's using Grover's algorithm in order to find as a as an optimization algorithm. and if it's using a quantum data. So still, it's very useful in machine learning or artificial intelligence, precisely because whenever you do machine learning or artificial intelligence, you are trying to optimize something. And quantum computing is very good at doing that. And I think this is the final sample, which is the quantum simulation. When there are uh, problems in nature that we want to understand. Okay, so for example, the one that I gave here is the protein folding problem. Okay, so protein folding is very important because a protein that folded wrongly, especially when in a human body, um, uh, they give rise to various diseases. Okay, like mad cow's disease, um, and um, and other diseases in the brain. Okay, so now to now to be able to now if you want to simulate this behavior, um, it's very resource intensive if you only have a classical computer, because for a system with 47 spin one half particles, okay, so there are 47 particles, you need about 2 to the 47 bits to record the state. Okay, 2 to the 47, and according to this, it's about 20 terabytes of data storage. Now all of this data uh, need to be in memory. Okay, so well, my laptop only has 32 gigabytes of memory. Okay, that uh, usually most laptops only have 16 gigabytes. Okay, but imagine 20 terabytes of RAM. Okay, that's it's really a lot. Okay, but if you have a quantum computer, then you only need 47 logical qubits, okay, to store the same information. Okay, but let's not go into the but creating a logical qubit is very hard. Okay, so um, let's not go into that. But the thing is, you only need 47 qubits to store the same information. So as you can see, 2 to the 47 versus 47, that's a logarithmic speed up, or logarithmic in terms of space needed. Okay, so use cases. So in healthcare, you can use it to simulate chemical reactions to create new drugs, okay, protein folding, personalized medicine. In finance, used in portfolio optimization and fraud detection. Yeah, because all of these are something to do with special number two, number one, number two, something to do with optimization. Number three has something to do with pattern matching, which is quantum computer is very good at. And here, applied to blockchain and cryptocurrencies. So blockchain, the people that are into blockchain are now, they're very aware now that they need to convert into what is known as the post-quantum cryptography methods because of the impending, impending attack on the traditional crypto systems. Yeah, and also quantum key distribution, which I discussed earlier. So that's for cybersecurity. machine learning. So all of this, logistics. So because quantum computing is very good at optimization, then companies like DHL and Volkswagen, they're already experimenting on using quantum computers in order to optimize their operation. And also in manufacturing design, okay, still because of optimization, Airbus uses quantum annealing in order to model uh, design design efficient wing design, the airplane. So Daimler and Samsung for build better batteries. So simulation, quantum chemistry. Yeah, so this one here, identifying shortest wiring, also optimization. And I think this is the final slide I have. It's agriculture. So there is this problem. So agriculture is very important because we all need to eat, and in order for us to produce food, then we need fertilizer. Um, but to manufacture fertilizer, you need ammonia. Okay, but to manufacture ammonia, then you need a big resources plants. Okay, so ammonia plants, which need a lot of resources and power in order to operate. But um, but nature is, nature is able to manufacture ammonia very efficiently. Like for example, there are some bacteria that live in the roots of the plants that are able to create ammonia almost without effort. Okay, it's because of this molecule here called nitrogenase. Okay, which is at the moment beyond the ability for supercomputers to simulate. That's why it's hard to understand it. But with a quantum computer, it may be possible to be able to simulate and understand this molecule. Okay. Okay, that's it. I think for your questions, we'll do that later. I will now give the floor to Asher to give a short demo on how to do how to program a quantum computer using IBM QISKit. So I'll give the floor to you, Asher. Okay, hold on. Probably I will need to unmute you. Oh, can you talk?
Hello, guys. Can you
Okay.
hear me, guys?
Yes.
Nice. That's nice presentation, Sir Bobby. So for now, we will be moving on to our demo session, and that is how to use IBM QISKit to create your quantum circuits. So let me turn off first my video, and then share my screen. Let's share the screen. Okay, share it. Okay. Are you guys able to see the screen? Hello, guys.
I'm
Are
able
you able to
to
see it?
I'm able to see the screen.
That's nice. Okay. Okay. So what we're going to do now is to create quantum circuits and also understand the basic quantum gates. So this activity can be done on a platform. So this is called the Google Colab. So this is made by Google. And what is interesting about this is you can actually have a free account on them. And also a good thing is your computation. You can perform computation on this platform for free. Sometimes they give you a higher disk and RAM capacity. And if you're on a premium plan, of course, you have a higher uh, resources. And the caveat only is this Google Colab platform utilizes Python. So gladly, IBM QISKit, which is the framework that we're gonna be using to create quantum circuits, is based on in Python. So uh, it's all good. So of course, let's start with the very first introduction here, which is the quantum logic gates. So a quantum logic gate are the building blocks of quantum circuits. Like classical logic gates are for conventional digital circuits. So if you remember, we have classical logic gates, or for those that doesn't know it yet, classical logic gates are composed of AND, OR, NOT gates, and these gates is something that powers up our current classical computers. Let's have a simple example. Let's say we work with a NOT gate on our classical gate, right? So let's say we have a light that is switched off, and if we apply an X gate, it will turn on. Secondly, if we have a light that is turned on, and if we apply a NOT gate, what will happen is the light will turn off. And if we want to map it to our computers, so we know that the computers today is, of course, made up of 1 and 0. The processes, the softwares that's running our computers is made up of 1 and 0. So let's say we have a binary one, we have one, and if we apply a NOT gate, it will become 0. And if we have 0 as a bit, if we apply a NOT gate, it will become 1. So actually, these numbers, these binary numbers, are what makes up the things that you are seeing here in the screen, like the letter A, for example. A is actually represented as 01000001 in Unicode, in binary. And the numbers that you're seeing here, the image that you're seeing here also, and of course the video that you're currently viewing now are all made possible because of the logic gates. So currently, we have another set of gates, which is known as quantum logic gates. So instead of performing quantum gates on classical computers, we have gate that performs computation on quantum computers. So for here, we have X gates that gets the opposite of what the state of the qubit is. So let's say the qubit is from state 0. If we apply an X gate, we're gonna have a state 1. Okay. We also have a Hadamard gate. Let's say that we have a state, that we have a qubit, we have a 1 qubit, and we apply a Hadamard gate. It will create a superposition of the state 1 and 0 in it. So it have the probability of occurring either a 1 or a 0. And also, we have further gates here like the CNOT gate and the CCX gate. So this is a control NOT gate. Okay, so without further ado, let's start by going into our exercise 0, which is importing the required files. So to do that, let's just follow this instruction here. So according to here, let's run the code below, and then let's use this to import our libraries. So this is the code that we'll need to run. So let's click this run button here. So as you can see here, Google Colab actually downloaded all of the libraries, and using its resources, it's also the one that build the images and build the libraries as well. So currently, what we're doing here is we are importing the framework to create our quantum circuit, which is QISKit. And that's the most important part here. This one these things here are something that makes our program looks better and easier to manipulate. But what you need to actually import is this one, QISKit framework. Okay, so after you click run, as you can see, the library is already satisfied in the notebook and looks like it's already been imported. Okay, so for our exercise number one, what we're gonna do is to create a simple basic circuit. So let's see here, it says copy and paste the code below, run the code to show the circuit and simulate. So we're gonna see first, what does the circuit look like? What is the layout of the circuit? And simulate it. What will be the result of that circuit? And yeah, sharing the result. Okay, so to do that, let's copy paste this one and then put it here and then paste it. So before we run it, as you can see, we are importing the required libraries, which is, of course, this one. We have QISKit. We're importing quantum circuit. So we can create our own quantum circuit. We have the classical register, and we have also the quantum register. And this will also import our simulator, which is IBM Air. Actually, you can use a real quantum computer here. You just navigate to IBM Quantum Computing Lab, and there you can actually utilize a real quantum computer. But for here, what we're gonna do is to use a quantum simulator, which is known as the QISKit Air. Okay, so so let's start. On this code, we are creating a input quantum register with 1 qubit. So to do that, we need to have a variable. It could be anything that you want and any name that you're thinking of, and you are going to assign it to this the value that the function will return. Quantum register, then the number of the qubit you wanted to create. So currently, we're just gonna create 1 qubit, and then also we're gonna create a classical register with 1 bits that will hold the result of the measurement. So to do that, we're gonna assign a variable, and then it will gonna give us the return of this function, the result of this function. And also, this will initialize a quantum register in our circuit. And after that, we're gonna create a quantum circuit. So remember that we have a register that we define. So that's very important. Registers needs to be defined. Then after that, we will be initializing our quantum circuit. So it could be any name that you want, and then you have this function quantum circuit, and then the names, the variable names of your registers, which are in this case, we have Q in and C, which will be our quantum register, input register, and our classical register. And this is actually optional. This will create a barrier, like a drawing, a line drawing in our circuit, so that it will really looks much neater. But if you don't prefer it, you're free to delete that. So, and this one will actually measure the result, and then it will draw it. But so for now, let's run it. Okay, it's now running. So the output of this one should be the layout of our quantum circuit. Okay, it's now running. Oops. Okay. So as you can see, we got we have duplicate image, but these are just the same. But let's just focus on the first result. As you can see, we have a we have a 1 qubit input register here. This is what we define in this code. And then we have here the barrier in this one. And then also we measure it. We measure the input qubit register, and then we outputted it into our classical bit. So as you can see, we measure our first input qubit register, and then we output the results into our classical bit. Okay, great. So the next part is we're gonna simulate our quantum circuit. So to do that, we're gonna have this function here, and this will actually utilize the Ayer, the simulator that we imported a while ago, and this will calculate what will be the result. This will simulate the result of our quantum circuit. So we already initialized the function. Then let's try to simulate, and what will be the result? So let's just type simulate, and it takes the parameter of our quantum circuit. So let's click run. Okay, as you can see here, we got a output of 0. Okay, so when we simulate our circuit above, we get an output of 0. The reason for that is because in IBM and QISKit, the initial state when we create a qubit is state 0. So if we create a 5 qubit input register, we have 0, 0, 0, 0, 0. If we create 2 qubit input register, we have 0, 0. If we create 1, we got 0. So by default, it's all initialized to 0. Okay, great. Then we have another instruction here. It says here, modify the code and apply an X gate on the first qubit and see the results. So let's try to do that. So what we're gonna do in this diagram here is we will be applying an X gate before we measure it. Okay, so let's try that. And what will be the result after we apply the X gate? So to do that, let's apply the X gate before the barrier. So you have your uh, quantum circuit, and to apply an X gate, you just use X. And what qubit do you want to apply that X gate for? So you want to apply it on to this one qubit here. So one qubit, the first qubit is actually represented by indexes. So we reference it as 0. So let's click run. Okay, now we got here the X gate. And the next thing that we need to do is to actually measure it. So a while ago, we have here a 0, right? So what will happen since we already apply our X gate? Let's see. Great. As you can see, we have now 1 as a result. So remember a while ago when we were talking about NOT gates, we have it switches it flips it from 1 to 0, or from 0 to 1. So as you can see, we apply an X gate here, and by default, every qubits that we create are initialized into 0. Then if we apply an X gate, it will turn to 1, and that will be the output of the measurement. Okay, it's nice. Okay, for our exercises number 2, for the second exercise, what we're doing here is we are creating an input register with 2 qubits, a classical register with 2 bits. We initialize our quantum circuit and we draw it. So let's see the result. Okay, so if we click run, as you can see here, we have 2 input quantum register. This is the first one, and this is the second one. And then we created a barrier, which is this one. So the barrier spans uh, the entire circuit, okay? And then we perform a measurement, which is all quantum register input well, the input quantum register, which is the first qubit and our second qubit. Okay, so what do you think will be the result of this? Okay. So to actually see the result, we just click, I would just type simulate and it take a parameter, which is your circuit. So let's guess the result. The result should be, since by default, qubits are initialized to state 0, and if we measure it, should be 0, 0. So let's click run. Well, as you can see, we got here 0, 0 as the result. Now, uh, we have here the exercise. Modify the code to create a circuit with an input register of 3 qubits, an output register of 1 qubit, and a classical register of 3 qubits. So let's do it one by one. Let's create an input register of 3 qubits. Let's modify the code above. And then let's change it to 3. And then according to here, an output register of 1 qubit. So if you want to create another set of register, just type here any value that you want, and then quantum register 1, and then classical register of 3 qubits. So currently we have here 2 classical bit, so we'll just change to 3, and let's see what will the output be. What is the layout of our circuit? Okay. As you can see here, our quantum output register is not shown, right? Because we need to include that on our quantum circuits. So let's just add our other quantum register and click run. Hope it does work. Now it does work. So as you can see here, we have our first 3 input register, this one, and this one. We have our other register that we define, but we didn't measure, which is this one. And then we have we have 3 classical bit here, 3 classical bit. So that's nice. Now let's move on into the heart of quantum gates, which is the Hadamard gates. So according to the instruction here, use the code below to add a Hadamard gate to our first input qubit. So let's see. Let's copy this one. And then, as you can see, we only define 1 qubit. We only define here 1 bit. So according to here, we need to add this Hadamard gate. So to do that, let's just paste it here. Oops, what happened? Where we are? Okay, let's just type it again. QC.H, then our input quantum register. Then we only work with the first qubit, which is on our index 0, right? So let's see what will be the layout of our quantum circuit. So as you can see here, we have a Hadamard gate already, our barrier, and then we'll measure it. So as discussed a while ago, we know that the Hadamard gate create a superposition on our state. So if you got a state and if you apply a Hadamard gate in it, it will create a superposition of 0 and 1. Is really that true? So to find out, we need to simulate it. Okay, let's just delete this. Let's simulate it and see what will be the result. Is it really true that Hadamard gate create a superposition of 0 and 1? Let's see. Right, that's true. It's a fun fact. It's a legit fact. We have here a result, an output of 0 and 1. Okay, nice. And actually, this kind of quantum gate allows you to create algorithms, and if you create an algorithm, you can perform a lot of very nice applications already, because you're not just only working with two binary numbers, right? You're not just working with 0 and 1. You're working with the values of 0 and 1 uh, in a superposition. Okay. So the next one we have here the exercise 4, which is the superposition. So as you can see here, we wanted to create this following circuit. So what we're gonna do is to create two quantum register, and we measure it, and then we apply a Hadamard gate in it. So what we can do is to just copy paste the code above. I don't want to type it again. And then let's create a new code here. Let's try to put this into code. So we have two quantum register that we want to create. And then we have uh, 2 bits, right, for our classical register. So this is important, so we can actually get the information from our qubits. And then we apply a Hadamard gate onto our first qubit and to our second qubit. So our second qubit is on our state, I mean, on our first index. Okay, first qubit is our 0th index. The second is on the first index. And then let's run it and see if we're gonna get this output above. All right, so as you can see, it's just the same. We got this one. Nice. And what do you think will be the result if we simulate it? Okay, let's see what will be the result if we simulate it, since we have already 2 qubits here. Okay, so let's see. As you can see here, we have now 4 results, which is 0, 1, 2, and 3. Right? We have 4 results: 0, 1, 2, and 3. Okay, that's really nice. Okay, and then the next one is, let's see here, that we're gonna modify the code below with the 2 input qubits and 2 classical bits, then apply a Hadamard gate. So actually these instructions, we've already done this. So it's just here, we have already applied this already. Nice. So for our last exercise, right, we already tackled our first 2 gates, the X gate, we have our Hadamard gate. Now, for our last exercise, let's work with the control NOT gate. So this is simple. The idea here is if the control qubit, if the control qubit is 1, then it will flip the value of the target qubit. If the control bit is qubit is 1, then it will flip the value of the target qubit from 0 to 1. Again, if the control qubit is 1, it will flip the value of the target qubit from 1 to 0. So let's try this one. So first, let's construct this circuit. So we have here 2 quantum register. We have a barrier, right? We have, of course, the classical register. We have the barrier here. And then we have the control NOT gate, which is this one. So it takes 2 parameters, which is the target, I mean, the, the control qubit, which is currently our first qubit, and the target qubit, which is our second qubit. So what do you think will be the result here? So as you can see, let's try to run it first. So when we, of course, we go back again, if the result is 1, I mean, if the control qubit is 1, then the target qubit value will be flipped. Okay, so as you remember, every qubit is initialized to 0. If it's 0, it will do nothing. So is it really true? If this is 0 and this is 0, will the output be 0, 0? So let's try to do that. Let's click simulate and run it. Yes, we got 0, 0 here. And then let's follow this instruction above. What if, right? What if the control qubit is 1 and the second qubit is 0? Will it flip our second qubit since this is 1? The control qubit is 1. So let's try that. So to do that, of course, we first need to apply an X gate here, right? On our first qubit, we need to apply an X gate so that it will become 1. So 0, make it 1, let's apply an X gate. So let's apply it on our first qubit. So to do that, let's do QC that X, our first qubit's index is 0. And then according to here also, the second qubit must be 0. So we don't need to do anything. So by default, it's 0, initialized to 0. So let's click run. And nice, we got this one. We now have 1 and we have 0. So if we apply an control NOT gate, will it change this 0 to 1? Will the output become 1, 1? So is that true? So the only way to find out is to actually simulate it. So as you can see, we have here 1, 1. That's nice. And for our last example, how about we apply an X gate on our second qubit? So of course, we apply an X gate on the first qubit. Let's apply an X gate on our second qubit and see what will be the result. So will it flip this is the value of this from uh from 1, right? So this is 0, this is 1. So okay, this is 1. So will it become 0, 1? Will it become the output? So let's see. Hopefully it's our output. So you can see we have here 0 and 1. And yeah, that concludes the end of the exercises. And thank you. And of course, if you want to go on with other exercises like a good algorithm, we got the Bernstein-Vazirani block box circuit. We have this Bernstein-Vazirani verification exercise. We have this actual Bernstein-Vazirani problem we got here. And if you also would like to get on the challenge, we have here the full adder circuit that allows you to use quantum gates to create a full adder circuit using quantum gates. So yeah, that's all for now. And thank you guys very much.